So we reach some sort of dynamic equilibrium, which is going to be dictated by KSP. KSP is going to be the products over the reactants, the activities. The activities of the products, so those will be pretty much close to the molar concentrations. The activity of the reactant here, this appears solid, so the activity is 1. And so the KSP is just equal to the silver ion concentration times the chloride ion concentration. What we do in this particular case is we assume that nothing's dissolved initially. And then we put some solid into the water and see what the maximum amount that dissolves. So some will dissolve here and some will dissolve here. And then we wait for it to equilibrate so we get the maximum. X would be the maximum amount of silver ions and chloride ions we would get in solution. And so it turns out that we end up with something like this. The solubility of silver chloride. There are different ways we talk about the solubility. One is qualitative. Chlorides, bromides, and iodides are all insoluble, right? Actually, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. And so qualitatively, it should be insoluble. Silver chloride's insoluble. But what does insoluble mean? Insoluble means, according to our book, that less than 0.1 moles of it dissolves in a liter. Well, 0.1 moles is actually quite a lot, and so, well, obviously we're going to have less than 0.1 moles per liter dissolved. That means it's insoluble, but this is very qualitative. When we look at it quantitatively, we want to know the max amount that dissolves. And the max amount is going to be given in 2 typical units: grams per milliliter, grams of solid per milliliter of water, or molar solubility. You know, how many moles? Is it less than 0.1 moles per liter, or is it more than 0.1 moles per liter? Because if it's less than 0.1 moles per liter, we call it insoluble. If it's more than 0.1 moles per liter, we call it soluble. Soluble is greater than 0.1 moles per liter. If it's about 0.1 moles per liter, we call it slightly soluble. Slightly soluble, which is about 0.1 moles per liter. Well, for silver chloride, it's less than. People have measured it, and so we can figure it out. Well, what is it exactly? Well, once we get it, we can figure this out, because over here, it turns out that the solubility of silver chloride, which I'll just label S, the solubility of silver chloride is going to equal the molar concentration of silver chloride I can get. So how many moles of silver chloride can I get to dissolve in a liter? Well, because of the mole ratios, for every mole of silver chloride that dissolves, I get 1 mole of silver ions. And so this is going to be equal to the molar concentration of silver ions in solution, which is equal to the molar concentration of chloride ions in solution. And so rather than calling this X, what we could do is we could call this S instead of X. And so at equilibrium, we're going to have S molar and S molar, because S is just the same as the solubility of the silver chloride. And so what we'll do here is we'll just saturate a solution, measure its solubility, plug those solubilities in here, and determine it. And so lots of people have done this, and they come up with a number of 1.8 times 10 to the minus 10 for the KSP of silver chloride. And that means the solubility must be the square root of that, which is, I think, 1.34 times 10 to the minus 5 molar. Well, 1.34 times 10 to the minus 5 molar is way less than 0.1 molar, so it's highly insoluble. Okay? And so somebody did the solubility measurements. They did the solubility measurements and then calculated the KSP. But once somebody does the experiment and calculates the KSPs, then we can compile those into a table and we can use these. Well, how can we use these KSPs? Well, we can use the KSPs to make certain kinds of predictions. For example, here, let's say I have 0.100 molar silver nitrate. And I'm going to add some chloride to this to precipitate it out, maybe as sodium chloride. And so if I have 0.100 molar silver nitrate here, I want to precipitate out all the silver ions. So the question is, how much chloride must be added to precipitate all the silver ions? So, well, if I add 0.100 molar chloride, will that do it? So in other words, I want to get rid of all the silver ions in this. I have 0.100 molar silver. Let's say I'm dealing with 1 liter. And so I have 1 liter of 0.100 molar silver nitrate. Well, how much chloride will I need? Well, this is going to be 0.100 moles. So I have 0.100 moles of silver. If I add 0.100 moles of chloride, then that should do it, shouldn't it? Okay, so let's try it. And so what I'm going to do is I'm going to do this. I'm going to add the chloride, and then I'm going to avoid solution dilution. The way I'm going to avoid solution dilution is I'm going to make this both 0.100 molar chloride and 0.100 molar silver ions. And so if I have 0.100 molar chloride and 0.100 molar silver, then it's stoichiometric. If it's stoichiometric, I should completely precipitate it out, right? Okay, so then we go to our KSP. Our KSP, now we want to do precipitation. So I do silver ions plus chloride ions. This is going to precipitate out silver chloride. I have 0.100 moles of this, 0.100 moles of this. This is going to go to 0, 0, and it's going to precipitate out 0.100 moles of silver chloride. But we don't do it like this. You know, even though this is a precipitation, when we do a precipitation, we look at the KSP equation and visualize this going backwards. That's the way we do it. And so this looks like dissolving, but it's both. It's dissolving and precipitation. The precipitation part is looking backwards. And so initial, I have 0.100 molar silver ions, 0.100 molar chloride. And so this should go to 0 molar and 0 molar, right? And I'm checked. That's good. Is that right? It turns out it's not right, because I want to double check my equilibrium. If I double check my equilibrium, the KSP is 1.8 times 10 to the minus 10. And so if I double check my equilibrium concentrations, I get a KSP of 0, which means I have 100% error. Right? A 100% error is, that's not good. And so, yeah, this is not right. And so let's repeat this. It turns out that I need to think of this as a equilibrium problem. And that is, if I start off at 0.100 molar, I compare QSP versus KSP. And QSP is going to be much greater than KSP. In other words, I calculate the reaction quotient, Q. And therefore, this has got to shift to the left. And so I'm going to lose minus X molar or minus S molar. In this case, it's got to be minus X, because S is for the solubility. Solubility is the maximum amount dissolving. We aren't dissolving anything, we're precipitating. And so this is the amount precipitated, or concentration precipitated. And so at equilibrium, I'm going to have 0.100 minus X, 0.100 minus X, and then I can solve for X. X is going to tell me how much precipitated. And so I can do that here. KSP is going to equal 1.8 times 10 to the minus 10, which is going to equal 0.100 minus x squared. Will the simplifying assumption work here? A simplifying assumption won't work here because if I use it, we have no x to solve for. And so I got to use the quadratic. So this is actually, oh, actually I could just take the square root. That'd be even easier. We'll take the square root of both sides, and then we get an x equal to times 10 to the negative 2. .99% to the negative 2. So this is going to be 0.100 minus 0.0999. This is going to leave me with, in other words, I'm going to precipitate out 99.9%, not 100%. I want to precipitate out 100%. And so it's kind of weird because I added the right amount. This is the right amount of chloride, right? But because of this equilibrium, it didn't all precipitate out. And so let's try something else. Surely, if I do this, if this solution were 0.100 molar silver ions, I'm going to take some concentrated HCl. What was the molarity of the concentrated HCl that you used? 12 molar. Let's make this 12 molar chloride. So if I use 12 molar chloride, that's definitely going to precipitate out all my silver, isn't it? Let's try it now. I'll do silver chloride solid. This is going to give me silver ions and chloride ions. All right, solids are just, activity doesn't change, so it stays 1. And so the silver ion concentration is 0.100 molar. The chloride ion concentration is 12.0 molar. And then I'm going to precipitate it out. Minus x molar, minus x molar. X is the amount precipitated, or concentration precipitated. 0.100 minus x, 12.0 minus x. And then see how much precipitates out from this. So let's go ahead and do the calculation. That means the KSP is going to equal 0.100 minus x times 12.0 minus x. And this is going to equal 1.8 times 10 minus 10. Here, I can't take the square root, unfortunately. But I can use the quadratic. So this is going to give me x squared minus a minus. So this is going to be minus 12.1x plus 1.2 is equal to 1.8 times 10 to the minus 10. And then subtract this from both sides. It's going to be 9 zeros. Is that right? is equal to 0. And so what does x come out to? Okay, what? Okay. It can't be 12 because that would give me a negative. So x is equal to 0.1. And so it worked, right? This is equal to 0.100 minus 0.1, which equals 0. And this would be 12.0 minus 0.1, which would be 11.9. And so I did it. I mean, precipitated out 100% of my silver ion. It just took 12 molar. Maybe we could have done it with 6 molar, right? But there's a problem. The problem is, well, I want to double check my answer. And so let's go ahead and double check my answer. When I double check my answer, does the K match that K? No. The K is way off. And so what did I do wrong? That x must be wrong. Did we make any assumptions? No, we used the full quadratic. And so what went wrong? The x has got to be wrong because our k's don't match. Double check didn't work. No, it's not because we're working with molarity. It's because, does somebody know what happened? Where the error is? It cannot be 0.1. The KSP value is too small? Well, we use K's at 10 to the minus 10. 10 to the minus 14, we've used K's at 10 to the minus 14. That wasn't too small.
Well, when doing the quadratic calculator, it automatically rounded to small. Yeah, rounded.
Okay. You know what the problem was? This doesn't work. This is wrong. And the problem is, this is a problem due to round-off error. And it's your calculator. This is calculator round-off error. The calculator is rounding the number. And so you might say, oh, this is not my fault. It's my calculator's fault because it's rounding it. Therefore, I can't get the right answer. But that's not an acceptable excuse because you should try to do what? To avoid calculator round-off error. The problem is it's because K is too large. K is small in the forward direction, but it's too large in the reverse. Which direction are we going? We're going in the reverse direction. K in the reverse direction is 10 to the positive 10, roughly. And so that means in the reverse direction, we're getting 99.9999999% reaction. If we're getting 99.999999% reaction, your calculator is going to round it to 100% reaction. Right? And so how do we avoid calculator round-off error? What's one trick we can use to get around calculator round-off error? Yeah, we could try successive. We just try successive maybe. But the problem is when you start punching in 99.999, it's going to automatically round it. And so one way to avoid that is by reset the initial condition. If we reset the initial conditions, then we can avoid this. And so I shouldn't have started that problem like this. What I should have done was this. Silver chloride is going to be in equilibrium with silver ions plus chloride ions. and I have 0.100 molar here and 12.0 molar here. This is my original initial conditions, and then I reset it. And so what I'm going to do is I'm going to reset this equilibrium to the left. So this is going to be minus y minus y. And so what is the limiting reagent here? The silver ions or the chloride ions? Silver, so that's going to go to 0. And then my chloride, well, y must be 0.1, so my chloride is going to go to 11.9 molar. Okay, now what I'm going to do is I'm going to let this equilibrate. And so this is going to be plus S molar plus S molar. The reason this is plus S is because this is the maximum amount that will dissolve here. In other words, I'm taking the solid and now allowing it to dissolve, but I have common ion now. And so this is called a common ion type problem here. And so at equilibrium, I'm going to get S molar and 11.9 plus S molar here. And this is going to avoid the problem of round-off error, because in the forward direction, I expect very little change, and your calculator should have no problem with that. And so we can reset, and then we end up with KSP is equal to 1.8 times 10 to the minus 10, which is going to equal S times 11.9 plus S. We make the simplifying assumption, and so this is S times 11.9, which gives us an S value of 1.8 times 10 to the minus 10 divided by 11.9.
Oh, I used to put the other solver.
Oh, did you?
Yeah, I know, 1.5.
Okay.
1, 2, that's 10 to the
Times 10 to the negative 11. Now this would have given us the same answer, you know, the simplifying assumption versus this, because K is so small. All right, so this comes out to 1.51 times 10 to the minus 11 molar, and then 11.9 plus S would be 11.9, and then we'd need how many? 10 zeros, 9 zeros, or 8 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, and then a 1, 5, 1. All right, now double check these. Does this double check out?